Hello, everyone. Welcome to chemistry class. This is your friendly host, Dr. H, and tonight I want to give you a lecture. Well, I want to have a little talk with you about what we call significant figures. And this is something which is very important in any science because any science involves making lots of measurements. And I'm here to tell you, measurements have problems. So I thought about this and I wanted to come up with a way to make this as relevant as possible to you. Well, what could be more relevant than a penny? I don't know if you know much about pennies, except for maybe you pick them up, maybe you save them. Some people don't even bother to pick them up anymore. But pennies before the date of 1982 used to be made of mostly copper. All right, they had a little couple percent zinc in there, but for our purposes, let's say it's all copper. In fact, we could say it's uh, 100% copper. You okay with that? 100% copper, which means what? Well, it means that it has to be made of all copper atoms. Nothing but copper atoms in here. Is that 100? Is that completely true? No, we know there's some zinc in there. But let's just say we have a very special penny. It's made of all copper, right? And you could actually look at these pennies. They look a little bit different than the modern day pennies do. Well, what do you know about atoms? You know that they're small. You know that they're spherical. Okay, they're round in 3 dimensions. They're spherical. Well, here's something you may not know. Any copper atom in the universe is identical to the next copper atom next to it. I know that sounded funny when I said it, but that's what I meant. Copper atoms are identical. The copper atoms in your penny are the same as my penny, are the same as the copper atoms in the penny on planet Mongo. They're identical. If they're identical in terms of diameter, and I am talking about diameter, then that means the diameter of one copper atom has to be the same as the diameter of another copper atom. And that brings up an interesting point. Could I measure if I knew how many copper atoms were from one side of a penny? So let's just change colors here for a second. Let's go to yellow. If I knew, if I could measure from one side of the penny to the other, the number of copper atoms, could I come up with the exact length of this penny? And I'm going to say, theoretically, sure. We have to know a couple things. We have to understand that atoms in any material obey very specific behaviors. What I'm saying here is copper atom. Let's try to change this to gold so it looks like a penny. That's as close as I'm going to get. There's one copper atom. Let's go a little bit bigger. Copper atom, copper atom. No, no, no. Back, back, back. I might as well just use black. Okay? In any material, atoms sit right next to each other. And in our penny, I have one copper atom lined up next to the other copper atom. I didn't mean to put a space there. Through the entire structure. There's no overlap. There's no spaces, just one copper atom sitting next to the other. And in fact, I'm going to come up with a number right now. Let's just say, for the heck of it, there's 75 million copper atoms. How do I know this? Well, I know the name of the guy that made the penny. Okay, so I assume from this side to this side, exactly 75 million copper atoms. Do you buy that? Okay, fine. It's actually pretty close to the actual number, right? 75 million atoms. Now, here's where I have to make a little bit of a stretch. Let's say I know the diameter of a copper atom exactly. Turns out they're so small, we just can't measure them exactly. Well, let's just say I did. Okay, let's say I did measure it exactly. All right, so here we go. If I knew the diameter of copper, by the way, the best that we know the diameter of copper is 256 picometers. This is a picometer. A picometer is basically 1 times 10 to the minus 12. So if you want to convert that into a unit you're more familiar with, meters, it's 256 times 10 to the minus 12 picometers. Sorry, meters. But let's say I knew the diameter of the copper atom exactly. And I just kind of made these numbers up. I added all these numbers in. All right. If you can buy that, we can go on to the next topic. So listen to this. If this penny is made of nothing but copper atoms stacked one atom next to the other, there's 75 million of them. Each atom has this diameter. Can't I take these two numbers and multiply them to calculate, not measure, calculate the exact length of this penny from this side to this side? The answer is yes. So I can do a little math problem here. I can take these two numbers, 75 million atoms multiplied by 256.15311762153 times 10 to the minus 2, and I get the answer of 1.92114838 times 10 to the minus 2 meters. Well, let's get that back into a more realistic number. If you multiply that number by 1,000, you get it into millimeters. And I think people are pretty familiar with about how big a millimeter is. And here it is. It's 19.21148382216 millimeters. So that's the exact diameter of a penny. Pretty cool, huh? Well, I have a problem. And I want to pause for a minute to show you my problem. Okay, so what I've done here is taken a penny and I've kind of dropped a ruler onto the screen. Well, it's kind of hard for you to see right here, so I'm going to make my penny bigger. There it is. Penny and ruler are now huge. And I come over here and I adjust my ruler and oh, something's wrong. Something is wrong. I calculated this exact diameter of the penny. When I come over in here and measure it, what's the best that you can do? Maybe I should zoom it in a little bit more. Gigantic penny. It looks like a little bit bigger than 19. Each of these derivations here is a 0.1. Maybe I'm somewhere between the 19 and the 0.1. So I can kind of like, I mean, maybe. So maybe the best I can do here, or maybe it's a little bit bigger. Maybe it's like 19.2. So maybe I can say with the best of my ability with this ruler that this penny is 19.2 millimeters. Uh, what happened here? How come I didn't get all these extra decimals? What's the problem? Am I not a good measurer? Maybe I need to go to measuring school? I'm a pretty good measurer. I went to college. Now there's a problem here that no one in this room or no one listening to this can actually overcome. The problem lies with our ruler. We don't have a ruler good enough. It's not the fault of the ruler. You simply can't fit that many derivations in between here. If you tried to, you'd go blind because you couldn't see them all. So this underlies the problem with making a measurement. The exact answer. And remember, this is a theoretical. We took a few liberties with this. This is the exact answer for the length of the penny. When I measure it, I get this. So which of these do you think is more uncertain? If you're saying this one, then you are on the money. In fact, any measurement you make from measurements of volume, mass, what else is good? Volume and mass. Those are things we do in chemistry class. Time are always estimates of the exact value. They are always jam-packed with this. They're packed with uncertainty. Okay, so 8 minutes into this little lecture, I have an answer for you. We have to have a way of representing the reality of real measurements. The fact that our number here has some issues. Okay, so I have to be able to look at this number and ascertain the number of significant figures or significant digits that this number has. I had a college class a couple years ago, and they really didn't like that definition. And what they came up with instead is I think a good alternative to this is how many meaningful digits this number has. So what we're going to talk about now are the rules for how to go and determine the number of meaningful digits any number has. Because let's face it, chemistry class is chock full of measurements. Okay, I'm going to change gears. Okay, so this is why we do this. Let's talk about something like density. I know you all know what density is. Density is equal to the mass of an object divided by its volume. Mass over volume. Okay? So let's say I go to a laboratory scale and I measure the mass of an object to be 7.11 grams. That's a realistic number for something we would get with one of our scales. Our scales only give us 2 decimal places. And I divide it by, let's pick a volume. Let's say I measure a volume of 1.13 milliliters. Now I want you to go and actually divide those two numbers. Okay? Just use your calculator, divide those two numbers, and see what you get. Now remember our discussion before about uncertainty in measurements and exact numbers versus a measured number, and apply that to here. Okay? I'll wait just a second. Okay, that was a second. Now the answer you get from your calculator. I love this. You ready? 6.292035. Wait for it. 5398. I got a couple more. 23. And this would be units of grams, grams per milliliter. We have a problem. Houston, we have a problem. Something happened between these two nice little humble numbers that we measured versus the number that we did what? We calculated. Something happened. The calculator that you own is not a bad calculator. It works fine. The problem is it has no idea what it's doing other than to calculate numbers. It doesn't know anything about uncertainty. So when I talk about the rules for significant figures, you will know that you have to look at the beginning numbers. Okay, this number has 1, 2, 3 significant figures. This number has 1, 2, 3. So my answer can only have 1, 2, 3 significant figures. Okay? The answer for this problem, correctly represented with all the error and all the uncertainty in these numbers, is 6.29, not this answer. So this is the rationale for using significant figures. The next lecture, I'm going to go through the rules. Okay? Thanks for watching. I'll see you later.